We are now on to chapter 21A. This is our first lesson on applications of differential calculus. So far we've looked at how to find some basic derivatives. So we've looked at the power property, where you drop the power down, multiply it to the front, to decrease your exponent by 1, and that finds your derivative function. Now we're going to look at some reasons why you might want to find a derivative. So what are some problems that we can solve by finding a derivative? Our last two sections from our last chapter, I think it was maybe E and F, they covered slopes of tangents. So we wrote equations of tangent lines, and we wrote equations of normal lines to curves. So that's one thing you might want to do with your derivative function, is find the slope of your tangent line. But there's some real-world problems that we can also solve with this as well. So the first thing we're going to do with our derivative is use it to help us determine where a function is increasing versus decreasing. So when a function is increasing, that means it's going up from left to right. So if you look at this parabola, as we go from left to right, if you think about it as a ball being thrown, here the height of the ball is increasing. There's a point right here called the local maximum where the ball then turns around and begins to decrease. It begins to get closer and closer to the ground. So this point, it turns around and it comes back down. In our last section, we learned that our derivative is 0 here. This has a slope of 0. Your tangent line at this local maximum has a slope of 0. Any point over here where it's increasing, the tangent line will be going up. And any point over here where it's decreasing, the tangent line will have a negative slope. Okay. So if we look down here at identify the interval where the function is increasing and decreasing. So we look at our line from left to right. In order to go from increasing to decreasing, or vice versa, you have to stall out for a second. You have to get to a slope of 0. So in order to go from going up to going down, there has to be a moment, just this little moment here, where you're not doing either. So this is where the ball gets thrown up. It stalls out just for a second before it comes back down. There has to be a moment wherever it reaches 0 slope, 0 rate of increase. So it's positive increase, 0 for just a second, negative increase. So for question 1, intervals where the function is increasing and decreasing. If I follow this line from left to right, this is barely increasing, and then it begins to increase quicker and quicker and quicker and quicker. This line is increasing from left to right. The whole thing is increasing. So this is increasing always. So we would call this an increasing function, because it is always increasing. Function, how about that? Function. A decreasing function will always be getting smaller, and then some functions vary. So for part B, we have an upside down parabola. So if I followed this line from left to right, right here, my point is moving up. There's a moment right there where it sort of stalls out before it starts to go down. So this is going up. Right there. It's increasing. This point right there, it stalls out for just a moment before it starts to go back down. Right here, my line begins to go down. So how do we write the interval where the function is increasing and where it's decreasing? So for increasing, that's my blue piece. You can write this in two different notations. You can write it in interval notation or set notation. We worked with both of these notations when we talked about domain. So for interval notation, this is increasing all the way to the left. So starting out here, all the way until x gets to 2, which is that point where it stalls out. So in negative infinity all the way to 2 is where our function is increasing. And decreasing starts at the 2 and goes to infinity. So from here on, it's decreasing. Increasing we can also write in set notation. So it's all x such that x is less than 2. And for our set notation for decreasing, it'll be all x such that x is greater than 2. Traditionally, in most textbooks, especially American textbooks, we don't put a line here because at this point it's neither increasing or decreasing. It's just stalled out for just a moment. I don't really understand why, but this textbook's just a little bit different. It's not correct or incorrect one way or the other. It's just fine. You can either leave no line or put a line. It doesn't matter. Okay? So if you want to put a line, go for it. If you want to put a bracket, go for it. Oops, sorry, a bracket there. It doesn't matter. Include it or don't include it, because at this point we really don't know what's happening. It might be increasing, it might be decreasing, so include it or don't include it, doesn't matter. Okay? Traditionally, you'll see that I won't include it. That's just because the majority of the textbooks that I've worked with, that's how they keep their notation. Alright, for question C, we're going to look at where this function is increasing and where it's decreasing. It looks like it curves around a lot. Sometimes it helps to pick out the points where it's stalled out. So right here, it turns around. It goes from increasing to decreasing. Right here, it goes from decreasing to increasing. So those are some critical points. If you look at your x values, those are the critical points where it changes sign. It changes from increasing to decreasing or vice versa. So I'm going to break it up into both. So for increasing, it's going up here. That should have an arrow on it. Then it goes down, and then it goes back up again. So although my arrow is pointed down, from left to right, this is going up. Here it's going down. There it's going up. So for increasing, this one's pointed to the left, so from negative infinity to 1, or sorry, negative 1, and 1 to infinity. It's increasing on two different intervals. This one, that one. In set notation, this would look like all x such that x is less than negative 1 or x is bigger than 1. We include this piece where it's smaller than negative 1 and this piece where it's bigger than 1. For decreasing, this is happening between those points right here. It's kind of like a slide. From left to right, it's going down. So this is between negative 1 and 1. So for interval notation, negative 1 to 1 like this. For set notation, it's all x such that x is between negative 1 and 1. Negative 1 is less than x, which is less than 1. Means x is between negative 1 and 1. So how does this relate to the derivative of the function? Well, the derivative finds slopes, and if we know the slope, it finds slopes of the tangent line. If we know the slope of the tangent line, then we know whether it's increasing or whether it's decreasing. If the slope of the tangent line is positive, we know the function is increasing. If the slope of the tangent line is negative, we know the function is decreasing. If the slope of the tangent line is 0, that's that kind of in-between point where we don't really know what's happening. So let's look at this question number 2. Find the intervals where that is increasing or decreasing. I'm going to start by graphing this on my graphing calculator. Y equals negative x to the third. My function looks like this. I'm going to graph it. Second graph brings me to a table. So negative 2, 8, negative 1, 1, 0, 0, 1, negative 1, and 2, negative 8. Okay. This function appears to always be decreasing. So if you look at it from left to right, it appears to always be decreasing. Now there's a chance somewhere in here maybe it changes. In order for it to change, we know for sure over here it's decreasing, it's going down. And we know over here it's for sure going down. But there might be a piece in here where it ends up going up. In order to figure this out, we have to notice that in order to go from increasing to decreasing, or vice versa, we have to reach zero slope for just a moment. In order to go from increasing to decreasing, we have to reach zero slope. The point where it reaches zero slope is called a critical value. Our critical values are where our derivative is equal to 0. So it's a little definition. That is where a critical value occurs. It's where our derivative is equal to 0. This is just our function notation for derivative. F prime of x is equal to 0, or dy over dx equals 0. Okay, those mean the same thing. This is function notation. This is y equals notation. So let's take our function and let's find the derivative. So that's my original function. We want to find f prime of x, which means our derivative function. We take our exponent and drop it to the front. So we'll get negative 3x. The 3 drops down to a 2. I want to find the value for x, or see if there is a value for x, where this slope, remember this is our derivative function. It's our slope function, our gradient function. I want to see if there's a point where the slope is 0. So we're going to say 0 equals negative 3x squared. We can divide both sides by negative 3. And in order to solve 0 equals x squared, square root both sides. Square root of 0 is 0. It'd be plus or minus 0, but that's kind of pointless because positive 0 and negative 0 are both 0. So that's saying that at this point right there, at the point when x is 0, our function has 0 slope. So I should have drawn my line where it's sort of, I don't know, it's a little flatter right there where it has 0 slope. But my line is close enough for this. So that's the point where it has 0 slope. However, that's the only point where it has 0 slope. And we can see that on the left and on the right, it's negative on both sides. We can draw a little diagram to help us with this as well. We put our critical values on the diagram. So 0 was our critical value. And we're going to check both sides of it to see whether the function is increasing or decreasing on both sides of it. So I'm going to pick a number that's a little bit smaller than 0 and a number bigger than 0, like negative 1 and 1, and plug them into my derivative function. Negative 3 times negative 1 squared tells me that my slope here is negative. If I plug in positive 1, it shows me that my slope is also negative. So that tells me that my function is always decreasing. So it goes negative, stalls out for just a moment, and then negative. It is always going down. Additionally, from the graph of your function, if you remember, you can second calculate number 6. You can find the slope over here and see that it's negative. Oops. Go to the left, wherever you want. It's negative 8.69 there. And if you go to the right, the slope over to the right side of it is also negative, negative 8.69. Okay, so it's negative on both sides. So this would be called a decreasing function. so it's always decreasing. All right, let's look at the next one. So I'm going to graph y equals 2x cubed plus 3x squared minus 12x minus 5. Looks all right. I'm going to do second graph, and I'm going to plot my points. Negative 3, 4. Negative 2, 15 will be way up here. Negative 1, 8. 0, negative 5. This is very steep. 1, negative 12 will be down here. 2, negative 1. And that's the last one. If you look back at your graph, it looks like that. So I'm going to try to do this mostly visually. We can also set our derivative equal to 0, but that's quite a bit of work. So I like to save myself some work whenever I can. So from left to right, my function appears to be going up right here. Then it turns around, it comes back down before it ends up going back up again. So it's increasing on 2 different intervals, and it's decreasing in between. We need to find these points where it decides to turn around. So one option is to find the derivative and set it equal to 0. That's quite a bit of work. So let's see what else we can do with our graphing calculator to figure that out. We've found minimums and maximums on our graphing calculator before. That's what this point is considered. It's considered a maximum, local maximum, and this is considered a local minimum. So we can find those without using the derivative at all. So second, calculate maximum. I'll find this point first. We take our little dot, we go to the left side of it. So my dot kind of goes off the screen. If you want to zoom out, you can. I want to zoom out probably around the origin just so it's pretty symmetric. So I'm going to get my little cursor around the origin. So you can zoom out if you want. Now we're probably zoomed a little too far out, so zooming in is probably a little better. However you prefer. If you want to, you could change your window also. So you could go to your window and be like, oh, I need to look a little lower and a little higher. And then you can go back to your graph. Depending on how fluent you are with your calculator, trying to see it is a good idea. Second, calculate a maximum. So I'm going to get my cursor right on that maximum point. Then I go to the left of it, because it says left bound, enter. Around to the right side of the maximum, enter, enter, and it says it's at, that's negative 2, 15. So this point, that was also in my table, but it's good to know that is the maximum point. We can also calculate our minimum point. So we come around here. My minimum value is this lowest point of the valley. Go to the left of it, enter. Go around to the right of it, enter, enter. And it tells me it's at 1, negative 12, which was also in my table, but it's good to check. So my function is increasing from negative infinity to negative 2, and from 1 to infinity. Notice I always use my x values for this. It's decreasing in between, so from negative 2 to 1. In set notation, if you prefer, it's all x, such that x is less than negative 2, or x is greater than 1, or all x such that negative 2 is less than x, which is less than 1, implying that x is between negative 2 and 1. The IB exam would be fine if you wrote x is between negative 2 and 1. So if you don't like that notation, you can write it in words, and they're totally fine with that. Alright, I think most of these end up at good points. If not, just always double check that minimum maximum thing in your calculator. And this gets you set up to do Chapter 21A. Your homework assignment is posted on Canvas. Thanks for watching.